All right, let's dive in. Today, we're putting on our detective hats to crack a classic case from the world of algebra, the polynomial puzzle. You know, those equations that look kind of intimidating? Well, we're on a mission to find the hidden values of x that make the whole thing tick. So, let's start the investigation.
You've been there, right? Staring at a problem, a puzzle, and it just feels like there's no way in. That's exactly what solving polynomials can feel like. It's a mystery, complete with hidden clues and some very elusive suspects. But here's the good news. Today, we're learning the investigative techniques that will crack the case, every single time.
And here it is, our first case file. The equation is x cubed minus x squared minus 4x plus 4 equals 0. Looks a little complicated, but our job is simple. Find the values of x that make this whole statement true. These values? They're the culprits we're looking for.
Now, in detective speak, we call these culprits zeros or roots. Think of it this way. If you were to graph this equation, the zeros are the exact spots where the line crosses the x-axis. They are the solutions to our mystery, and our job is to hunt them down.
Okay, so every good investigation starts with lining up the potential suspects, right? You can't just guess randomly. You need a system, a way to figure out who could have possibly done it.
And our first huge clue comes from something called the rational zero theorem. This thing is like getting a hot tip from an informant. It takes a literally infinite number of possibilities and whittles them down to a nice, manageable list of suspects that could be our zeros. It's a total game changer.
And the rule for finding these suspects? It's surprisingly straightforward. Every potential rational zero can be written as a fraction, p over q. The top number, p, has to be a factor of the constant term. That's the number at the very end without an x. The bottom number, q, has to be a factor of the leading coefficient, the number attached to the x with the highest power.
So let's apply this to our case. The constant term is 4. So the factors for p, plus or minus 1, 2, and 4. Easy enough. Our leading coefficient is just 1. So the factors for q are just plus or minus 1. Now, we divide all our p's by all our q's and voila! Our suspect list is just plus or minus 1, 2, and 4. We went from infinite possibilities down to just 6 potential culprits. Now we're getting somewhere.
All right, we've got our suspects all lined up. Now for the fun part. It's time to take them into the interrogation room and see which ones crack under pressure.
So our main interrogation method is based on two closely related ideas. First, the remainder theorem. It basically tells us that if we divide our polynomial by, say, x minus k, the leftover remainder is the same as if we just plugged k into the function. But then, the factor theorem takes it one step further. It says if that remainder is 0, we've found our culprit. K is a 0. So listen, this is the most important part. A remainder of 0 is a confession. It's the gotcha moment. If we test one of our suspects and the math works out to 0, that number is, without a doubt, a 0 of the polynomial. It's basically a mathematical confession.
But, how do we check that remainder quickly without doing a bunch of messy long division? Well, we use a slick technique called synthetic division. Think of this as our polygraph test. It is a super fast, clean way to divide and find that crucial remainder.
Let's run a test on our first suspect, x equals 1. We just write down the coefficients from our polynomial. 1, -1, -4, and 4. Okay, first step, bring down that first one. Now, multiply it by our suspect, which is 1, and add it to the next number, -1. That gives us 0. We do it again. Multiply that 0 by our suspect, add to -4, we get -4. One last time. Multiply that by our suspect and add to 4, and what do we get? 0. That's the confession. The remainder is 0, which means x equals 1 is a confirmed root.
So we found one of our culprits. But is that the whole story? What if there are more solutions hiding in the shadows? Sometimes you gotta dig a little deeper and look for the hidden clues.
And this brings us to a huge foundational law in mathematics, the fundamental theorem of algebra. It's a guarantee that every single polynomial equation has at least one solution. Now, here's the twist. Sometimes that solution is a complex number, one that involves I, the imaginary unit. This opens up a whole new dimension to our case.
But it gets even better. This theorem actually means that a polynomial will have exactly the same number of zeros as its degree. So a third-degree polynomial, like our x cubed, you guessed it, it has 3 zeros.
A fourth-degree polynomial? It's going to have 4 zeros. We just have to be willing to look for complex numbers and also count any roots that might show up more than one.
And when we do find one of these complex zeros, there's a really cool rule. It's called the complex conjugate theorem, and it says they never work alone. If a number like a plus bi is a 0, then its conjugate, a minus bi, is automatically 1, too. They're partners in crime.
So quick question for you. Let's say we're investigating a case, and we discover that the imaginary number I is one of the zeros. Who else has to be a 0? Come on, you know this one. That's right, its partner, negative I. They always come in pairs.
Okay, we've gathered all our tools, we've got our suspect list, our lie detector test, and we even know about those sneaky hidden partners. So now, let's put it all together and crack a real-world case.
Here's our next case file. A local bakery needs a cake pan, but it has to have a very specific volume, 351 cubic inches. They've given us some clues too. The length is always 4 inches more than the width, and the height is exactly 1/3 of the width. Our job is to find the dimensions.
So when we take all that information from the bakery, the volume, the length, the height, and translate it into algebra, it all boils down to this one equation right here, where W is the width of the pan. The mystery is now in a language we know how to speak.
We just follow our process. Step 1. Line up the suspects. The rational zero theorem gives us a list of all the factors of 1053. Now, since a cake pan can't have a negative width, we only need to interrogate the positive suspects. We start testing them with our lie detector, synthetic division. We try a few, and then we test the number 9. And what happens? We get a remainder of 0. Bingo! The width has to be 9 inches.
And once we know the width is 9 inches, the rest is a piece of cake. The length is 9 plus 4, which is 13. The height is 1/3 of 9, which is 3. We've got our answer, 9 by 13 by 3 inches. Case closed.
You know, as we've seen, the culprits we find, the zeros, they can be all different types. Some are nice, clean, rational numbers, like 1 or 9. Others might be irrational numbers. And some, as we now know, might be complex, hiding out in the world of imaginary numbers. But our detective toolkit lets us find them all.
And look, this isn't just about solving abstract puzzles or designing cake pans. Polynomials are the language used to design bridges, to model financial markets, and even to plot the course of rocket ships. You now have the fundamental tools to decode that language. So the only real question left is, what mystery are you going to solve next?